Hi everyone. Now we are going to discuss about the second session of the stereochemistry of organic compounds. Myself Sumalata S, Assistant Professor from the Department of Chemistry, SKNG GFG College, Gangavati. Now in this session we are going to discussing about the enantiomers, diastereomers, meso compounds, racemic mixture, racemisation and optical isomerism in the tartaric acid. Okay, let's begin. What are these enantiomers and diastereomers? We know that when we stand in front of a mirror, what happens? We will going to see a reflection on the mirror, right? Our right will be reflected as in the left in case of mirror image, and the left will be reflected as a right in case of mirror image, right? So when we superimpose these mirror images, these are not the superimposable. Why? Because our right is as a left in the mirror and left is as a right in the mirror image. So those images are termed as enantiomers. Okay, what are the enantiomers? Enantiomers represent the non-superimposable mirror images of a molecule. Okay, for example, see here, this is the D-glyceraldehyde and this is the L-glyceraldehyde. Here what happens? The molecules, both the molecules are same, but there is only difference in this case. Okay, here hydrogen is in the right side and OH group is in the left side, but here OH is in the left side and hydrogen in the right side. Okay, both are identical one, but they are difference in the arrangement of atoms, and these are mirror images. These are called as the enantiomers. When we going to superimpose, means this is kept on this molecule, means what happens? This OH will superimpose on the hydrogen and this hydrogen will superimpose on the OH. So not identical one. So this type of non-superimposable mirror images are termed as enantiomers. Okay. Similarly, here this is the L-glucose and this is the D-glucose. What happens? These two are identical one mirror images and these are termed as enantiomers. On the other hand, the diastereomers represent the non-superimposable non-mirror images of each other. Means what happens? These groups, okay, these are same molecular formula, same structural formula, but differ in the spatial arrangement, and these are not the mirror images of each other. Those are termed as diastereomers. Okay, enantiomers means enantiomers are the non-superimposable mirror images, whereas diastereomers are the non-superimposable non-mirror images. Similarly, see here, these two are enantiomers of each other and these two are enantiomers each other. And what happens? This is the one, this is diastereomer with this structure and this structure. Okay, this first one is enantiomer with the second one, but first one is diastereomer with the third and the fourth. Similarly, the third one is enantiomer with the fourth, but third one is diastereomer with the second one and the first one and the fourth one. Okay, these are termed as diastereomers and enantiomers. Okay, next coming to the meso compounds. What are these meso compounds? A meso compound is an achiral or optically inactive compound that contains chiral centers. Even though they contain chiral centers, but they possess an internal plane of a symmetry. Okay, that possesses an internal plane of a symmetry that renders it superimposable on its mirror images. Similarly, see here it is the 2,3-dichlorobutane. Here what happens when we taking this example, here this consisting of, this one is the one chiral carbon, means it is attaching one hydrogen, one CH3 group, one Cl group, and other one is the another bulky group. So this is the chiral carbon, and here also this is the chiral carbon. Even though this is consisting of the two chiral carbons, this is consisting of the plane of the symmetry, means this plane, it can divide this molecule into two equal halves, and these are mirror images of each other. Hence this type of compounds are called as meso compounds. Okay, whereas enantiomers and diastereomers are the optically active compounds, but this meso compounds is consisting of the, because of the plane of symmetry, this is optically inactive. Next, racemic mixture. What is the mean by racemic mixture? A racemic mixture is a mixture containing the equal amounts of two enantiomers, okay, which are non-superimposable mirror images of a chiral molecule. Means here, see here, this is the R lactic acid and this one is the L lactic acid. What it means? R means this can rotate the plane polarized light towards clockwise direction or the right direction, right side. This is called as the R isomer. Whereas this is the S lactic acid, means this can rotate the plane polarized light in anti-clockwise direction. Okay, so this is the S isomer. The mixture of this R isomer and the S isomer is termed as a racemic mixture, means 50% of the R isomer, 50% of the S isomer. What happens in the resulting case? This is rotating the plane polarized light in the clockwise direction, and this is rotating the plane polarized light in the anti-clockwise direction. This is consisting of the, this is we are taking 50% and this we are taking 50%. So 50%, 50%, both they are cancelled out each other, and these are not having the ability to rotate the plane polarized light. Hence, this racemic mixture becomes optically inactive. Okay, what is this racemization? Racemization is a process that converts an optically active compounds into a racemic mixture. The process of making the racemic mixture is termed as racemization, means which is consisting of the 1:1 mixture of two enantiomers. This involves the loss of optical activity. Okay, because why? Because one compound rotating the light in the right direction, other compound rotating the light in the left direction, both are cancelled out each other. Due to this, these compounds are optically, mixture of these two isomers are optically inactive. Next, optical isomerism in the tartaric acid. Okay, so tartaric acid is an organic compound with the molecular formula C4H6O6, and the structure of this compound is given by this one, and it has a two chiral centers. One is this one, other one is this one. Okay. To understand the optical activity of this compound, we can draw it in the seahorse structures. Okay, these are the seahorse structures. Here, this one is a one chiral carbon, and this is the other chiral carbon. Okay, this is the D lactic acid. Sorry, this is the D tartaric acid, and this one is the L tartaric acid. Okay, we can here. The above compounds are optically active as they have no elements of symmetry like sigma, plane of the symmetry, and I, center of symmetry, alternating axis of symmetry, simple array, proper axis of symmetry. Any elements of symmetry are absent here, means this is the optically active compound. The compounds are asymmetric with the two chiral centers. As we can see, the above two isomers are the mirror images of each other, and these are known as enantiomers, and these are the two optically active isomers of the tartaric acid. The first one is the D-tartaric acid, means which rotate dextro-tartaric acid, which rotate the plane polarized light towards the right side or clockwise, whereas the second one is the L-tartaric acid, which is the levo-rotator, means this rotate the plane polarized light towards the left side or the counter-clockwise direction. Okay. Besides these two enantiomers, the tartaric acid also has an optical isomer which has a center of a symmetry. Although it has a two chiral centers, it is optically inactive. Means it is having the plane of a symmetry or a center of a symmetry. This molecule is optically inactive. That is, this is the meso-tartaric acid. Hence, the tartaric acid has three optical isomers, out of which two are optically active enantiomers and the other one is the optically inactive meso compound. Okay. And by this session, we came to know that enantiomers, diastereomers, racemic mixture, racemisation and optical isomers of the tartaric acid. Thank you.